This will be our last video on electron configuration. We'll spend more time on maybe a little bit on shorthand, a little bit on some of the exceptions, and deal with orbital diagrams in a little bit more detail. So we will always in my class use the periodic table and do the electron configuration filling order of electrons, which is what I'm covering. You need to understand on the periodic table there are different regions and you have to know where everything is. So let's number this 1, 2, 3, 4, 5, 6, 7. Those numbers are horizontally, those are called the periods of the periodic table. If you're in period 1, the principal quantum number is 1. If you're in period 2, the principal quantum number is 2, and so on. Next, you need to understand the regions. In the white are the S regions, or cream colored. The P's are in the pink. The greens are the D block, and they're n-1, meaning if it's in the fourth period, this is actually 3D1, 3D2, 3D3, and so on as you go across. Once you get to here, this is 4P1, 4P2, 4P3, and so on. So D's are off by 1. And F's, they're down here. They fit in between 6 and 7 right here, and they're an n-2. So these are the blocks 1s. We remember helium actually fits over here electron configuration wise, but it's been placed here because it's a noble gas. So 2s1, 2s2, 3s1, 3s2, 4s1, 4s2, and so on. When we get to the P's, this is 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, because they're all in the second energy level, and you just go across. The D's, as I've stated before, are off by 1. So even though this appears to be in the fourth period, this is a 3D1, 3D2, and so on. And the F's, because they're off by 2, this is actually 4F1, 4F2, 4F3, and so on. And these are the 5F's down here. So when we look at the filling order, we can let them fill in there. So I've got my S, the P's, the D's, and we'll kind of let them fill in. So you can see the pattern one more time. And hopefully in your mind, you are calling those out as they're coming up and they make sense to you. Remember the D's are off by 1. I heard that person away in the back say, well, why does it go 3D3, 3D5, 3D5, and then 3D6, 3D7, 3D8, 3D10, 3D10? Well, we're going to talk about that. That's an exception to the rule. I want you to learn the rule, and then once you know the rule, then we're allowed to break the rule and talk about exceptions. Okay? So I'll let that finish up there. You can again, hopefully that makes sense, except maybe some of those ones in the D block might make a little not as much sense to you at this point, but hopefully they will here in just a bit. Notice again that the F's are off by 2 in each one of these. All right, so here we go. So if we look at the energy sublevels, and we've seen this diagram before, right? In the first energy level you have only S, in the second you have S and P, in the third you have S and P and D, in the fourth you have S and P and D and F. And if I were to draw them out, the nucleus belongs down here. This would represent the first ring of the atom, n equals 1, and you have only an s orbital. N equals 2, you have S and P. N equals 3, S, P, and D. N equals 4, S, P, D, and F. And notice that a 3D is higher energy than a 4S. So that means in the filling order, when you start, everybody, all the S's, you get 1 circle. All the P's get 3, all the D's get 5, and all the F's get 7. So if you're doing the filling order, you go from the bottom. 1S2, 2S2, 2P6, 3S2, 3P6, 4S2, 3D10, 4P6, and so on. And that's what I'm trying to show you here with the filling order. Now, we've gone through these rules before, but I need you to know them. Off-bow, that's sort of the Disneyland parking rule, right? Where you take the first available spot, you don't drive around. So it's German for building up. Electrons are added one at a time to the first available energy orbital, and then once those are full, then we move up higher. The next rule that we want to deal with is the Pauli exclusion principle. If you have an orbital, one of those circles, it can hold a maximum of 2 electrons, but they have to be spinning in the opposite direction or they will repel each other. And finally, Hund's rule, electrons will each go into a single orbital of what's called a degenerate or equivalent orbital. That means each of the p orbitals get one electron before any one gets two. Each of the d orbitals get one electron before any d orbital gets two electrons. That's what Hund's rule says. Now, if you remember the Bohr model, there are a certain number of electrons you can put in each ring, right? Each orbit, and it was 2, 8, 8, 18, and so on. And that corresponds with the quantum mechanical model. They don't argue about that. All right. Now, we've looked at this diagram before where we said, look, if you're doing hydrogen right here, it has one electron, it's a 1s1, spin up. If you're doing helium, it's over here. I know it looks like it's in the p block, but remember, helium fits here, so it's really a 1s2, 2 electrons. They both fit in that same orbital, spin up, spin down. Lithium is atomic number 3, it fits right here, so it has 3 electrons, 1s2, spin up, spin down, and 2s1. Beryllium is right here, element 4, so it has 4 electrons, 1s2, 2s2. Carbon is element 6, 1s2, 2s2, 2p2. So it goes up, up, not up, down in the first orbital. So we've seen this slide before as well. So we've done all of this. We know where the s, the p, the d, the f orbitals are. We can count all that stuff off, and we feel pretty good about all of those. At least I hope you can, because using the periodic table is how we're going to be reading those off. Now, this is the same, it's similar information. I just picked an element and I put the electrons. So fluorine has 7 electrons. So they go up, down, 1, 2, up, down, 3, 4, up, 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 5, 6, 7, 8, 9. So fluorine has, I said 7, it has 9 valence electrons. Excuse me, 9 total electrons. It does have 7 valence, but we're not talking about that right now. And so when looking at this, it's going to be a 1s2, 2s2, 2p, 2, 4, 5. And that's what it comes out to be. Okay? All right. Nobody commented, but look at here. See how this guy here? Let's go back a second. Nitrogen, it is 1s2, 2s2, 2p3, but this is a violation of Hund's rule. There should be 1 electron in each before we double up. So that's the violation. Now we'll go ahead and correct it, and notice it corrects itself. So it's still 1s2, 2s2, 2p3, but the way we filled it in is now correct. It wasn't before. Okay, let's see where we go next here. Rules, we've already said these, right? The off-bow says start from the bottom, work your way up. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, bottom up. That's the off-bow principle. Okay? The Pauli exclusion principle says if you have an orbital, one of those circular rings, you can get 2 electrons, but they have to be spinning in opposite directions. Kind of like a magnet. 2 magnets, north pole to north pole, will repel. When electrons move, they make magnetic fields. And finally, we end with Hund's rule, where it says if you have more than 1 orbital, everybody gets 1 electron before you add more. I'm not going to go through the spin here, inducing the magnetic fields. I think we've already discussed that with plenty of information before, but that's why we say they have a spin plus 1/2 and minus 1/2 as their quantum numbers. All right, if you're an S sublevel, right, there's only one type of s orbital. Each orbital can hold 2 electrons. When you're a p orbital, you can be a piece of x, piece of y, or piece of z. There are 3 p orbitals. Each one can hold 2 electrons for a maximum of 6. There's 5 orientations in space of the d orbitals. Each holding 2 electrons makes 10 max. The f's look a little bit like flower heads. There are a lot of lobes to them. There are 7 different f orbitals. Each can hold 2 electrons for a total of 14. Now, in terms of the quantum numbers, which again, I'm not going to ask you about, but if you want to know, n refers to the principal quantum number. That's the period on the periodic table, or the shell of the Bohr model, and those go by whole numbers 1, 2, 3, 4. The subshell is n-1, or L, and it goes from, if you're at 1, you can only have a 1, but if you have, it's n-1 for L, so n-1, 1 minus 1 is 0, is an s orbital. If you do a 2, then 2 minus 1 is 1, so you get 1, 0, and negative 1, and those are your 3 p orbitals. So anytime you see a 1, that's a p orbital. If you see a 2, then that's a d orbital from 2, 1, 0, negative 1, negative 2. Those are 5 d orbitals, and so on. And then the spin, of course, plus 1/2, minus 1/2. So again, I'm not going to worry too much about those quantum numbers at this point. If we are in an n equals 5 shell, it says what is the shell population? Well, if n equals 5, we can have L equals 0, that's an S, L equals 1 is a P, 2 is a D, 3 is an F. Now, theoretically, there is a G, although it's never been used. And then, of course, we have the M sub L is 0, and a spin plus and minus 1/2. That's an S. For the P's, we have P sub X, P sub Y, P sub Z, and then each of those gets a spin plus and minus 1/2. For D's, it gets really complicated, but you can kind of see the idea at F and G, and this will continue. So with 4 unique numbers, we get all the 4 quantum numbers that describe each and every electron in an atom. All right. I'm now going to show you a little shorthand way. I don't like this way. I'd rather have you read it from the periodic table. But if you can't figure that out, then do this. Write 1, 2, 3, 4, 5, 6, 7, S. Then go down a row and go 2P, 3P, 4P, 5P, 6P. Do another row, D, D, D. And then finally FFF. Now take out a red pen or black pen or whatever you want and start making little slashes. So, now they have to be slashed the way I'm doing them. Now, if you've done that, now you can connect. So it's going to say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and so on. And this will continue all the way through to finish out those orbitals. All right, let me keep going here. My phone's ringing. I'm hoping it's nothing important. I may have to pause this for a second if it keeps ringing. Now, I went ahead and added the number of electrons available in each orbital. Every time there's an S, I could put a 2 there, a P, I could put a 6, a D, a 10, and so on. So this is what oftentimes textbooks will show you as a way to figure out the electron configuration. Now again, when we've looked at this diagram before, well, we'll skip that for right now. Let's do shorthand, and even though we've hit this one before. If you say something ends with 3s1, and you have a periodic table in front of you, you'll realize you're in the 3rd energy level, the s orbital, the first square, that would be sodium. So this is sodium in shorthand configuration. In longhand, you would have written out 1s2, 2s2, 2p6, 3s1. What I put in brackets is the noble gas that precedes on the periodic table sodium. So that's the ones on the far right. So neon is 1s2, 2s2, 2p6. So by me writing this, I don't have to write all of this. And then I say what comes after it, 3s1. So again, if we look at what all those parts mean, that first part is the electron configuration of neon. Then it says we're into 3rd energy level. The orbital shape is a an s orbital in this case. And finally, there's 1 electron in that s orbital. That's shorthand. All right, we're going to kind of just review some things. There's the Pauli exclusion principle, right? Electrons, if you put them together in an orbital, have to be spinning in the opposite direction. Aufbau says start from the bottom and work your way up. So on the periodic table, it says we always start with element 1, 2, 3, 4, 5, and we go right in order across that periodic table. So the electrons fill the lowest energy orbitals first, that is the 1s, then they move to the 2s, the 2p, the 3s, and so on, from the bottom to the top. And then Hund's rule says that you're going to give, this is not allowed. You cannot put 2, 2, none. If you have 4 electrons, it goes up, 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 everybody gets 1, and then we double up, okay? And that's, we're calling it here the empty seat bus rule. I call it the creepy guy on the bus rule. If you're a young lady sitting on a bus late at night and there's 25 extra seats, somebody should not sit with you if they don't know who you are and you don't know them. All right, let's deal with some orbital diagrams and practice writing these. So here's a block from the periodic table, oxygen. It has an atomic number of 8, which means it has 8 protons. So as an atom, it has 8 electrons. So I know it has 8 electrons. So if I'm filling this up, I got 8s to fill in. So 1s2, so I'm going to go up 1, down. That's 2 electrons. I got 6 more to go. That's full, so I move to the 2s. So I go up, down. That's full. I've used 4 electrons. Now I go to the p orbitals, and I've used 4, and I got 4 more to go. So I put 1 in each. 5, 6, 7, up, 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 and then finally 1 has to go down, 8. That would be the correct way to draw the orbital diagram for oxygen. In terms of electron configuration, 1s2, 2s2, 2p4. Okay, the superscripted numbers represent how many electrons are in that particular orbital within that energy level, okay, on the atom. Longhand for sulfur. Sulfur has its atomic number 16, so it has 16 electrons. So if I had a periodic table in front of me, I'd write 1s2, 2s2, 2p6, 3s2, 3p4. Now add these up, the superscripted numbers. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12. So I need 4 more electrons. So I don't have to write 3p6, I'm going to write a 3p4, meaning that I've used 4 electrons in the p orbital. Now the outermost shell, signified by the highest principal quantum number. Here's a 1, these are 2s, and these are 3s. So the third energy level is the valence shell, has 2 plus 4, 6 valence electrons. And it will only be s and p electrons that we will concern ourselves with in all the other units. Everything else is called the core electrons or kernel electrons. In shorthand configuration, you write all the core or kernel electrons that were there, that's everything from the noble gas before, and you put it in brackets, and then write the valence electrons after. So we've already done this chart, I'm not going through that again. In terms of this example here, I'm going to skip that one. Let's just deal with this. Hydrogen, 1s1, hopefully that would make sense to you. When it's in the first period, it's in the S block. The yellow represents the S block, and there's 1 electron because it's in the first column. If it's in this one, it's going to be the second one, and so on. In shorthand configuration, we write the noble gas that precedes our element, the core electrons, and then everything else that follows. So let's pick germanium right down here. I've identified it in black. So we know it's going to end with 4s2, 3d10, 4p2, because we have to go in 2. So I need to find this noble gas right here, whatever that one is, right? So when I look there on the periodic table, that's argon. So when I write argon, that takes care of 1s2, 2s2, 2p6, 3s2, 3p6. That's argon. Then what do I have after it? Well, I have a 4s2 that I'll put here. Then I have a 3d10, remember they're all off by 1. And then finally I have a 4p12 to get there. And that would be germanium in shorthand electron configuration. Now, in terms of stability, atoms want to have 8 electrons in their outer shell, to have a full outer shell of electrons. That's called a stable octet. So if you can fill up the S level only, that's some stability. That's why helium's pretty stable. If you can fill up the S and the P, that's very stable, and so on. Half-full sublevels give a little bit additional stability. We'll talk more about that later on. All right, so what is this octet rule? Well, Octet refers to 8, so atoms are going to try to gain electrons if they are nonmetals, or if they're metals, they're going to try to lose electrons, and they do this until they have 8 valence electrons. Sometimes they don't make ions, instead they just share the electrons so they both feel 8. And that's what we call the octet rule, right? When an atom gets 8 electrons in its valence shell, it's satisfied the octet rule, and it will become very stable. I've said this a few times, I'll repeat it, only s and p orbitals are valence electrons. So there's 2s and 6p electrons, that's where the number 8 comes from. D's and F's are always part of the kernel, never part of the valence, so we don't worry about those, the D's and F's for the octet rule. Let's look at copper. Copper, we might expect to be, if you have a periodic table in front of you, argon 4s2 3d9. But actually it's argon 4s1 3d10. Now the reason for that is going to gain some stability with a full D sublevel. And I need to show you this, maybe some pictures. Chromium is the same example, but I want to kind of walk you through an example. So let's look here on the periodic table. So if we were doing this, we would have said 4s1, 4s2, then we would have said 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10. And that's what I showed you. But that's not the reality. Okay? If you remember back, we'll look at chromium and copper here. Okay? Instead, what happens, let's look first at copper. Notice that the 4s and the 3d are really close in terms of energy to one another, right? So they're super close. Now Mother Nature looks at this and says, well, I got 2 electrons in the 4s, and I got 1, 1, 1, 1, and 0 in the 3d, and says, that just doesn't seem right to me. So even though we might expect 4s2, 3d4 for chromium, what happens is we get extra stability if we have a half-full orbital. So what happens is Mother Nature promotes one of these electrons in the 4s and pushes it up to the 3d. Now, every one of these has 1 electron. None have 0, and that's more stable. And so we're going to call that 4s1 3d9. And when we would fill that in, you'll see it'll end up going 1, 2, 3, then it will go 5, 5, 6, 7, 8. Now the same game is played with copper right down here. It should be a 4s2 3d9, but again, you got 2, 2, 2, 2, 2, 1. Mother Nature says, you know what? I want all the D's to be equal, and promotes this 1 electron in the 4s up to the 3d. And what we end up with is a 4s1 3d10. So I'm going to take those and I'm going to convert them so it was not a typo when it said 1, 2, 3, 5, 5, 6, 7, 8, 10, 10. But had I told you that at the beginning of this discussion, your head would have exploded. Okay? Now, if on my test you missed the exception and you want to call it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'm not going to mark that wrong. Okay? As long as you have a general idea of electron configuration, you'll be okay. Now, if you go on to take dual credit chemistry or AP chemistry, we'll be sure that we learn the exceptions at that point. All right. I don't want to necessarily go into ion formation very much at this point. It turns out that some atoms will gain electrons, some will lose to get a stable octet. And when we do the bonding, I will bring that up in much more detail. So I'm going to kind of skip this part for right now. Let's go into here in orbital diagrams and practice some of these, okay? Because this is something that I will ask you on my test. So let's look at nickel. Nickel has 28 protons, so it has 28 electrons. So I'm going to put those in. So they go in, they'll go in up 1, 2, 3, 4, 5, 6, 7, up, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, everybody gets 1, 26, 27, 28. And that is the orbital diagram for nickel. Now, if I took the time to count the electrons, I could drop them down. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8 is the electron configuration of nickel. Now, what I want to do is kind of change things up a little bit. Now, I want you to look at this. If you take the time to count, there are indeed 28 arrows there. But I violated one of the rules. Do you know which rule I violated, or what am I showing here? If you look here, notice that there should have been an electron here for the 4s, and it got moved up to here. Well, this is called an excited state. This is where an atom, if the electron configuration does not go in order, but it seems to jump and leave a space, that's what we call an excited state atom. We'll talk more about that when we deal with light, when we deal with excited state electrons. Let's try another one. I've got, again, 28 electrons. Now, hopefully, something jumped out at you there that was in air. Okay? I'm hoping it was in the 3D region that you should be looking. Specifically right here, that's perfectly fine, isn't it? What about next to it? Can you have 2 electrons up? No way. What rule did we violate? Good. That is a violation of the Pauli exclusion principle. That cannot be written as such. And finally, let's look at this one. I've got 28 electrons. And again, I've made an error. Help me figure out where it is. Yep, it's in the 3D region. Notice I have 2, 2, 2, 2, and they all go up, down, up, down, up, down, up, down, and none. Right. No, that's not Aufbau, because they're in the right energy level. That's which rule? Hund's rule, right? Everybody gets 1 before we double up. So on the test, I probably won't just ask you a definition of Pauli exclusion or Hund's rule. I'll instead have you apply it in an orbital diagram. Now for fun, I'm going to give you a practice quiz. It won't count. It's just to see what you're doing on this, right? Well, let's do nickel next. I guess we just did. Is that one we just did? Yeah, we did that whole thing. I don't know why that one came up twice. So let's try this one now. Okay, it's not a real quiz, obviously, because you're watching it on tape. But what I want you to do is you can pause the video and try to take that and see what you come up with for answers. So you go ahead and pause, try to answer those, and I'll go through the answers with you once you start again. All right, that first one, nitrogen, if you had a periodic table, should have been pretty easy. It has 3, 4, 5, 6, 7 electrons, atomic number of 7, and that's what you should get. Silver, because it says complete, that's the longhand way, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9. Uranium you got to do in shorthand. The noble gas that comes before uranium is radon. So as soon as you put radon, you accounted for 86 of the protons. And then after that, 7s2, 61, 5f3. If you want to draw the orbital box for nickel, it should look like this. There should be 2 unpaired electrons at the end. The rule that states no 2 electrons could spin the same direction, the Pauli exclusion principle. If you're drawing a Bohr model of a titanium plus 4, that means you have to get rid of 4 electrons in the outermost shell to have that happen. And we'll talk about isoelectronic when we meet in person. All right, thanks for joining me, and we will continue our discussion of electron configuration with questions that you might have. Thanks for joining me. Bye-bye. Slowly, slowly, it's finally stopping, hopefully. I'm going to be bummed if that did not record.